The heat death of the universe is a slow ending. Over timescales measured in numbers that have more zeros than atoms in the observable universe, the expansion of space continues. Stars exhaust their fuel, black holes evaporate through Hawking radiation, and the universe approaches a state of maximum entropy, a featureless, cold, dark equilibrium in which no further processes are possible. Not because something catastrophic happened, because everything simply ran out. The heat death is the consensus prediction for the fate of the universe if dark energy is a cosmological constant, a fixed property of space that drives accelerated expansion at a constant rate indefinitely. The heat death is not the worst ending. If dark energy is not a cosmological constant, if it is something dynamic, something whose density increases as the universe expands rather than remaining fixed, then the universe does not end in cold darkness over quadrillions of years. It ends in a catastrophic expansion that tears apart every structure in the universe, in sequence, from the largest to the smallest, until nothing, not galaxies, not stars, not planets, not atoms, not atomic nuclei, not the quarks inside protons, can hold itself together against the expansion of space. This is the Big Rip. The Big Rip does not require exotic or implausible physics. It requires only that the dark energy equation of state, the parameter W that describes the ratio of dark energy's pressure to its energy density, be more negative than -1. The cosmological constant has W equal to exactly -1. A universe with W less than -1, what cosmologists call phantom dark energy, has dark energy whose density increases over time. As the universe expands, more dark energy appears. The more dark energy there is, the faster space expands. The faster space expands, the more dark energy appears. The feedback is runaway.
And the DESI first-year results, released in April 2024, showed a hint at approximately 2.5 to 3.9 sigma statistical significance that dark energy's equation of state may be changing over time, that it may not be a cosmological constant, that it may be evolving toward phantom territory. The DESI result is not confirmed. It may be a statistical fluctuation. The full 5-year dataset will determine whether the hint is real, but the possibility is currently consistent with the data. And if dark energy is phantom, if W is less than -1, the Big Rip is not a distant theoretical scenario. It is the fate of the universe on a timescale comparable to the current age of the universe. This video goes through exactly what the Big Rip is, what the physics requires, how the destruction unfolds, and what the endpoint actually looks like. There is something in the fourth section of this video that most people find the most disturbing. Not the destruction of galaxies, not the shredding of planets, but a specific calculation about the final moments before the rip completes. A calculation about what the universe looks like from inside, as every structure at every scale is torn apart simultaneously. That calculation produces an image of the final state that has no analog in human experience and no adequate description in ordinary language. Stay with me. Before we continue, the Big Rip requires dark energy with W less than -1. The DESI 2024 data showed a hint that dark energy may be evolving, possibly toward phantom territory. Drop a comment. Which ending do you think is more likely? The cold, slow heat death over quadrillions of years, or the violent Big Rip in 10 to 20 billion years? And which one do you find more disturbing? To understand the Big Rip, you need to understand one parameter: the equation of state of dark energy, designated W. W is the ratio of dark energy's pressure to its energy density. In standard physics, pressure and energy density are related but distinct quantities. For ordinary matter, the stuff of stars and planets, the pressure is much smaller than the energy density at cosmological scales, and W approaches 0. For radiation, photons, the pressure is exactly 1/3 of the energy density, giving W equal to 1/3.
For dark energy, the equation of state is negative. This is the defining characteristic of dark energy, a negative pressure that acts repulsively on the expansion of the universe. The question is, how negative? For a cosmological constant, vacuum energy, the energy intrinsic to empty space, W is exactly -1. The energy density of the vacuum remains constant as the universe expands. As new space is created by the expansion, the energy per unit volume remains the same, because the energy is a property of space itself, rather than a substance distributed in space. This constancy, W equals -1 exactly, means the cosmological constant drives accelerated expansion that increases in rate over time, but does so at a pace that allows structures to survive indefinitely. Galaxies eventually recede beyond the cosmological horizon. Stars eventually die. Black holes eventually evaporate. But these processes take the timescales of heat death, incomprehensibly long but not violent. The critical threshold is W equals -1. If W is greater than -1, if the equation of state is between -1 and 0, dark energy behaves like quintessence. Its density decreases as the universe expands, though more slowly than matter or radiation. The expansion accelerates, but at a decreasing rate relative to what phantom dark energy would produce. If W is less than -1, if the equation of state is more negative than -1, dark energy is phantom. Its density increases as the universe expands. As space grows, more dark energy appears per unit volume. The total dark energy content of the universe grows without bound. The expansion rate accelerates without bound. Phantom dark energy violates a condition in general relativity called the null energy condition, a constraint that is satisfied by all known forms of matter and energy, including the cosmological constant and quintessence. Phantom dark energy, with W less than -1, violates this condition. This violation does not make phantom dark energy impossible. The null energy condition is a classical condition, derived from general relativity without quantum mechanics. Quantum field theories can, in principle, produce effective states that violate the null energy condition on certain scales. Whether a consistent quantum theory of phantom dark energy exists is an open question. What is not open is the consequence. If dark energy is phantom, if W is less than -1, the Big Rip follows as an inevitable mathematical consequence of the equations of general relativity. The calculation is not speculative. It is a direct solution to the Friedmann equations, the equations that govern the expansion of a homogeneous isotropic universe, with phantom dark energy as the dominant component. The Big Rip is what the equations produce. The Big Rip was first analyzed in detail by Robert Caldwell, Mark Kamienowski, and Nevin Weinberg in a 2003 Physical Review Letters paper titled Phantom Energy, Dark Energy with W less than -1 and the Big Rip. The paper solved the Friedmann equations for a universe dominated by phantom dark energy and derived the timescale to the rip as a function of the equation of state parameter W. For W equals -1.5, the rip occurs approximately 22 billion years from now. For W equals -1.01, the timescale extends to approximately 1.5 trillion years. The sensitivity of the timescale to W makes the DESI measurement of W0 and W a critically important for determining whether the Big Rip is a relevant scenario. The Caldwell, Kamienowski, and Weinberg 2003 paper established the Big Rip scenario and derived the timeline to the rip as a function of the equation of state. For a constant equation of state of W equals -1.5, phantom dark energy with moderate deviation from the cosmological constant, the Big Rip occurs approximately 22 billion years from now. For W equals -1.1, a small deviation from the cosmological constant, the rip occurs approximately 120 billion years from now.
For W equals -1.01, an extremely small deviation, the RIP is approximately 1.5 trillion years away. The DESI first-year data, analyzed in the W0-WACDM parameterization, where W0 is the current equation of state and WA describes its rate of change, found best fit values that, in some dataset combinations, are consistent with a current W less than -1. The central values from the most significant DESI combination suggest a scenario that, if it were a constant equation of state, would correspond to a big RIP timescale of tens of billions of years. The DESI result is at 2.5 to 3.9 sigma significance, below the 5 sigma threshold for a confirmed discovery. The full 5-year DESI dataset will either confirm or refute the hint, but the possibility, a phantom dark energy scenario with a big RIP on a timescale comparable to the current age of the universe, is currently consistent with the data. Let's go through the timeline. For a specific phantom dark energy equation of state, W equals -1.5, giving a big RIP approximately 22 billion years from now, the sequence of destruction is as follows. The physics of the big RIP is governed by the Hubble parameter, the rate of expansion of the universe at any given time. As phantom dark energy accumulates, the Hubble parameter increases without bound. At some point, the expansion rate at the scale of any given structure exceeds the ability of the forces holding that structure together. That is when the structure fails. The sequence goes from largest to smallest. Galaxy clusters fail first, then galaxies, then stellar systems, then stars and planets, then atoms, then atomic nuclei, then, in the final moments, the subatomic particles themselves. 2 billion years before the RIP, galaxy clusters dissolve. Galaxy clusters, the largest gravitationally bound structures in the universe, are held together by the mutual gravitational attraction of hundreds to thousands of galaxies and the dark matter halos surrounding them. As phantom dark energy accumulates, the expansion rate exceeds the gravitational binding energy of the cluster. The cluster members begin to drift apart. The cluster ceases to exist as a coherent structure. This process is gradual at first. Individual galaxies at the cluster's periphery are the first to be pulled away. Over the following hundreds of millions of years, the cluster disperses entirely. What was a coherent gravitational structure becomes a collection of individual galaxies, moving apart at increasing speed. 2 billion years before the RIP is a long time by human standards, but it is only approximately 1.5 times the current age of the universe from the end. The dissolution of galaxy clusters is the first visible sign that the big RIP is underway. 60 million years before the RIP, galaxies themselves begin to dissolve. Individual galaxies, held together by the combined gravity of hundreds of billions of stars and the dark matter halos in which they are embedded, begin to lose their coherence. Stars at the outer edges of the galactic disk are pulled away. The spiral structure of galaxies like the Milky Way dissolves. Individual stars drift apart into intergalactic space. The Milky Way, if it still exists at this point, not destroyed in its merger with Andromeda approximately 4.5 billion years from now, begins to lose its outer disk stars approximately 60 million years before the Big Rip. Within a few million years, the galaxy dissolves entirely. What remains is a dispersed cloud of individual stars, each moving apart from the others at increasing speed. 3 months before the Rip, stellar systems dissolve. The expansion rate has now exceeded the gravitational binding energy of individual stellar systems, the gravity holding planets in their orbits around their stars. Planets begin to drift away from their host stars. The orbit of Earth, if Earth still exists, expands as the gravitational binding is overcome by the expansion of space. Within weeks, Earth's orbit has expanded beyond any recognizable relationship to the Sun. This is not a violent process at this stage. No explosion, no sudden rupture. Simply the slow detachment of planets from their gravitational anchors, as the expansion of space between them exceeds the gravitational force holding them together. 30 minutes before the rip. Stars and planets are torn apart. The expansion rate now exceeds the gravitational binding energy of individual stellar and planetary bodies. A star is held together by the gravity of its own mass, the inward pull of the star's mass on itself. The expansion of space between different parts of the star exceeds this self-gravity. The star expands rapidly as the space within it grows faster than gravity can hold it together. The expansion does not look like an explosion from outside. It looks like a rapid bloating, the star inflating as space inside it expands. Within minutes, the star's radius exceeds any stable configuration. Its material disperses. Planets undergo the same process. The rock and iron of a planet are held together not just by gravity, but by chemical bonds, electromagnetic forces between atoms. The expansion rate has not yet reached the scale at which electromagnetic forces fail. But gravity, operating over the planetary scale, fails first. Gravity was the force holding the planet's mass together as a coherent body. As gravity fails at the planetary scale, the planet expands outward, its material separating as the space between it grows. 10 to the negative 19 seconds before the rip. Atoms are torn apart. This is the threshold at which the electromagnetic force, the force holding electrons in their orbits around atomic nuclei, fails. The expansion rate has now reached a value sufficient to overcome the electromagnetic binding energy of atoms. Electrons are pulled away from their nuclei. Every atom in the universe simultaneously undergoes forced ionization, not from heat or radiation, but from the expansion of space between the electron and the nucleus. This is the moment at which the universe transitions from a place where chemistry is possible to a place where it is not. Every molecule, every chemical bond, every biological structure, every piece of information encoded in any material form, all of it is destroyed at this threshold. 10 to the negative 43 seconds before the rip, the Planck time. The expansion rate now approaches the Planck scale, the scale at which quantum gravitational effects become important and our current physics breaks down. What happens in the final 10 to the negative 43 seconds is not described by any confirmed theory. General relativity and quantum mechanics both fail at this scale. The Caldwell, Kamienowski, and Weinberg paper notes that at this point, the universe reaches a singularity, a point at which the physical quantities that describe the expansion become infinite and the equations that govern them break down. The Big Rip singularity is not the same as the Big Bang singularity. The Big Bang singularity is a singularity in the past, a point from which the universe emerged. The Big Rip singularity is a singularity in the future, a point toward which the universe evolves. In both cases, the equations reach a boundary beyond which they cannot be extended. What, if anything, lies beyond the Big Rip singularity is not knowable within current physics. The timeline of the Big Rip, the sequence in which different structures fail, was derived by Caldwell, Kamienowski, and Weinberg, 2003, from the relationship between the Hubble parameter and the binding energy of structures at different scales. The binding energy of a galaxy cluster is approximately 10 to the 61st ergs. The binding energy of a stellar system is approximately 10 to the 48th ergs. The binding energy of an atom is approximately 10 to the negative 11th ergs. As the Hubble parameter increases toward the rip, it sequentially exceeds the binding energy per unit volume of each structure, causing them to fail in order from lowest to highest binding energy density. Let's dwell on the final moments. Because the physics of the Big Rip's endpoint is strange in a way that goes beyond the sequence of structural failures. In the heat death scenario, the universe approaches equilibrium asymptotically, getting closer and closer to maximum entropy over infinite time, but never quite reaching it. There is no moment when the heat death completes.
There is no endpoint. There is only an endless approach toward a limiting state. The Big Rip is different. It has a specific endpoint, a finite time in the future at which the expansion rate becomes infinite and the equations produce a singularity. What does infinite expansion rate mean physically? The Hubble parameter, the expansion rate, describes how fast the distance between any 2 points in the universe increases. If the Hubble parameter is h, then 2 points separated by a distance d are moving apart at a speed of h times d. As h increases without bound in the Big Rip scenario, every pair of points in the universe is moving apart at an increasing speed. At some point before the singularity, the expansion rate exceeds the speed of light for points separated by any macroscopic distance. This is not a violation of special relativity. Special relativity limits the speed at which objects can move through space, not the speed at which space itself can expand. But it means that no signal, no light, no gravitational wave, no information of any kind can travel between points that are separating at superluminal rates. As the Big Rip approaches, the cosmological event horizon, the boundary beyond which no information can reach an observer, shrinks. Currently, the cosmological event horizon is approximately 16 billion light-years from Earth. As dark energy accelerates the expansion, this horizon shrinks. In the Big Rip scenario, the horizon shrinks to 0 at the moment of the rip. A shrinking horizon means the observable universe is getting smaller. Not because the universe is contracting, it is not. But because the expansion is carrying regions outside the horizon faster than light can cross the growing distance. In the final moments before the Big Rip, an observer's observable universe, the region from which they can receive information, shrinks to 0. The last photon that could ever reach them has already arrived. From that point, they are in perfect causal isolation, surrounded by expanding space on all sides, unable to receive any signal from anywhere. And then, within a fraction of a second, the atoms they are made of are ionized by the expansion. And then, within 10 to the negative 43 seconds, the subatomic particles themselves reach the singularity. The endpoint is not darkness, not cold, not silence. The endpoint is the complete dissolution of all structure at all scales simultaneously, followed by a singularity in the equations of general relativity that cannot be extended. If there is anything beyond the singularity, any subsequent state of the universe, any continuation, it is not described by any physics we currently have. This is the Big Rip. Not a whimper, not a slow fade. A final, simultaneous, universal structural failure at every scale, followed by a mathematical boundary. The shrinking of the cosmological event horizon in the Big Rip scenario was analyzed by Caldwell and Steinhardt in a 2003 Physical Review D paper. They found that the co-moving horizon, the boundary of the observable universe in co-moving coordinates, shrinks to 0 at the moment of the Big Rip, meaning that no 2 points in the universe can exchange information as the rip completes. This causal isolation is qualitatively different from the heat death scenario, where information exchange between nearby points remains possible indefinitely. The shrinking horizon in the Big Rip means that the last communication between any two observers occurs at a finite time before the rip, after which they are permanently causally isolated. Stop here. In the final moments of the Big Rip, an observer's observable universe shrinks to 0. The last photon that can ever reach them has already arrived. They are in perfect causal isolation, surrounded by expanding space, unable to receive any signal from anywhere, and then their atoms are ionized by the expansion. The endpoint is not darkness. It is complete causal isolation, followed by structural dissolution. Which part of that sequence do you find most disturbing? Drop your answer below. Let's compare the two endings directly, because the comparison reveals something important about what makes the Big Rip qualitatively different from, and in specific ways worse than, the heat death. The heat death is defined by increasing entropy. Every process in the universe, every star burning, every chemical reaction, every information processing event increases the total entropy of the universe. The second law of thermodynamics requires this. Over time, the entropy approaches its maximum value, the state in which no further processes are possible because there are no energy gradients to drive them. The heat death is not destruction, it is completion. The universe runs to its maximum entropy state and stays there. Information is not destroyed in the heat death. It is maximally dispersed, maximally scrambled, but it is conserved in the thermal fluctuations of the equilibrium state. In the heat death, quantum mechanics continues to operate. Virtual particles continue to appear and annihilate. Hawking radiation continues to emit from whatever residual black holes remain until they too evaporate. The universe is in equilibrium. Nothing happens, but the laws of physics continue to apply to the thermal bath that is the equilibrium state. The heat death is the universe at rest. Cold, dark, and inert, but physically consistent. The Big Rip is not rest. It is not equilibrium. It is a singularity, a breakdown of the equations that describe the universe, reached in a finite time. In the heat death, information is conserved in the thermal bath. In the Big Rip, information is destroyed, or rather, the concept of information ceases to be applicable at the singularity because the physical framework that defines what information means breaks down. In the heat death, quantum mechanics continues to apply. In the Big Rip, quantum mechanics, like everything else, fails at the singularity. In the heat death, space continues to expand. In the Big Rip, the expansion of space becomes the mechanism of destruction. The heat death is a conclusion. The Big Rip is a termination. The distinction is not merely philosophical. It has implications for questions about the long-term persistence of any information, any pattern, any structure in the universe. In the heat death scenario, extended to infinite time, there is in principle the possibility of thermal fluctuations spontaneously producing ordered structures. A Boltzmann brane, a self-aware structure arising spontaneously from thermal fluctuations, is an extraordinarily improbable event. But in an infinite time universe at thermal equilibrium, every improbable event occurs an infinite number of times. The heat death does not eliminate the possibility of spontaneous order on infinite timescales. The Big Rip eliminates this possibility. The universe does not continue for infinite time. It reaches a singularity in finite time. There are no infinite timescales available. Whatever has not occurred by the time of the rip does not occur. This is a meaningful difference. The heat death, as terrible as it is by conventional standards, leaves open the possibility, in an infinite future, of everything. The Big Rip closes that possibility at a finite time. It is worse than the heat death not because it is more violent, though it is, not because it is faster, though it is, but because it leaves no time. The universe ends at a specific moment, and whatever has not happened by then does not happen. The Boltzmann brane problem, the observation that in an eternal universe at thermal equilibrium, random fluctuations will produce self-aware structures more frequently than they produce ordered universes like ours, was first raised in the context of eternal inflation and the heat death by Sean Carroll, among others. The Big Rip scenario eliminates the Boltzmann brane problem by ending the universe at a finite time, but does so at the cost of ending everything else as well. The implications of the Boltzmann brane problem for the foundations of statistical mechanics and the validity of cosmological models are still debated. Now let's assess the current observational status. How likely is the Big Rip, given what we currently know? The answer requires distinguishing between what the data shows and what the data proves. The cosmological constant, W equals exactly -1, remains consistent with all current observations. The evidence that dark energy deviates from the cosmological constant is suggestive but not conclusive. The 2.5 to 3.9 sigma hint from DESI's first-year data is below the conventional 5 sigma threshold for discovery. It may be a statistical fluctuation, but the data is also consistent with phantom dark energy, with W less than -1. The current measurements do not exclude the Big Rip scenario. The constraints on W from the full combination of current cosmological observations, CMB from Planck, supernova data, baryon acoustic oscillations from multiple surveys including DESI, are approximately W equals -1, with an uncertainty of approximately plus or minus 0.05 to 0.1, depending on the specific dataset combination. This range includes values of W significantly less than -1. A value of W equals -1.05 is within the current uncertainty range and would produce a Big Rip approximately 500 billion years from now. A value of W equals -1.1 would produce a Big Rip approximately 120 billion years from now. These timescales are far beyond any human planning horizon, but they are finite, they are specific, and they are currently permitted by the data. The DESI full 5-year dataset, expected in approximately 2026, will constrain W to approximately plus or minus 0.02. This is a factor of 3 to 5 improvement over current constraints. At that level of precision, the measurement will either confirm the cosmological constant to very high accuracy or reveal a statistically significant deviation that would motivate the phantom dark energy interpretation. If DESI's full dataset confirms the hint, if the central value of W remains below -1 with 5 sigma significance, it would be one of the most consequential results in cosmological history. It would rule out the cosmological constant as the explanation for dark energy. It would confirm that dark energy is dynamic. It would open the question of the Big Rip as a serious predictive scenario rather than a theoretical possibility. If DESI's full dataset shows W consistent with -1, if the hint disappears with more data, then the cosmological constant remains the best description of dark energy, and the heat death remains the consensus prediction for the universe's fate. We are approximately 2 years from knowing which of these outcomes is more likely. 2 years from data that will substantially change our understanding of whether the universe ends violently in a finite time or slowly over quadrillions of years. This is the current state of the question. The constraint on the dark energy equation of state from the combination of Planck, CMB data, Type 1a supernovae, and baryon acoustic oscillations as of 2024 is approximately W equals -1.03 plus or minus 0.03 for a constant equation of state, consistent with the cosmological constant at approximately 1 sigma. The DESI first-year results shift the central value slightly and introduce a time-varying component that is at 2.5 to 3.9 sigma, depending on the supernova dataset used. The Euclid Space Telescope, launched July 2023, and the Vera Rubin Observatory's LSST, beginning operations in 2024, will provide independent constraints that will be combined with DESI's full dataset to produce the most precise measurement of the dark energy equation of state ever achieved. Let's step back from the physics and address a question that the Big Rip raises in a way that the heat death does not. The heat death is an ending on timescales so vast, 10 to the 100th years and beyond, that the word ending loses its meaning. Nothing we do now, nothing that has ever happened in the history of the universe, has any causal connection to what happens in the heat death epoch. The heat death is separated from us by a gulf of time so enormous that the entire history of the observable universe, 13.8 billion years, occupies a negligible fraction of the time remaining. In a heat death universe, the question of whether the ending matters is answered by the timescale. It does not matter in any practical sense because it is so far away that every chain of causation connecting the present to that future has been broken billions of times over by intermediate events. The Big Rip is different in this respect. If the Big Rip occurs in 22 billion years,
the Caldwell, Kamiankowski, and Weinberg estimate for W equals negative 1.5, then it is separated from the present by a time comparable to the current age of the universe. It is 1.6 times the age of the universe from now. This is not a time on which nothing could have a causal effect. In 22 billion years, stars that are currently forming will have completed their entire life cycles. Civilizations that do not yet exist could emerge, develop, and confront the Big Rip. The Milky Way and Andromeda will have merged. The resulting galaxy's stellar population will have aged significantly. The Big Rip is far enough away that it is irrelevant to any immediate human concern. It is close enough, in astronomical terms, that it is in principle within the scope of processes that have causal connections to the present. What does it mean that the universe ends at a singularity in finite time rather than approaching equilibrium over infinite time? Physically, it means that every structure, every pattern, every form of information that exists anywhere in the universe is destroyed at a specific moment, not dispersed into thermal equilibrium over infinite time. Destroyed, in the sense that the physical framework that defines what information means ceases to apply. Whether this matters in any meaningful sense is not a physics question. Physics can describe what happens. It cannot say whether what happens matters. What physics can say is this: the Big Rip, if it occurs, is the most complete ending that the universe could have. Not merely the cessation of interesting processes, not merely the approach to thermal equilibrium, the complete dissolution of every structure at every scale, followed by a singularity that terminates the equations that describe everything. The heat death leaves the universe intact but inert. The Big Rip does not leave the universe at all. The heat death is the consensus prediction for the fate of the universe if dark energy is a cosmological constant. The Big Rip is the prediction if dark energy is phantom, if W is less than -1. The current observational data is consistent with both. The DESI first-year results suggest a hint of phantom behavior at 2.5 to 3.9 sigma significance, below the threshold for a confirmed discovery, above the threshold for ignoring. If the hint is confirmed by DESI's full dataset, the timeline changes. The heat death, cold, slow, over timescales that make the current age of the universe look like a rounding error, is replaced by the Big Rip. Violent, sequential, complete. In 10 to 20 billion years, depending on the specific value of W, galaxy clusters first, then galaxies, then solar systems, then stars and planets, then atoms, then atomic nuclei, then the quarks inside protons. The observable universe shrinks to zero as the horizon collapses. The last photon arrives. Causal isolation is complete. And then, in 10 to the -19 seconds, every atom is ionized. And then, in 10 to the -43 seconds, the singularity. Not darkness, not cold. A singularity. A mathematical boundary beyond which the equations that describe the universe cannot be extended. The DESI full 5-year dataset is expected in approximately 2026. In approximately 2 years, we will know substantially more about which ending awaits. The universe does not adjust its fate to our measurement schedule, but our measurement schedule will adjust what we know about its fate. 2 years. One question. The Big Rip, if it occurs in 22 billion years, is approximately 1.6 times the current age of the universe away. In that time, every star currently forming will have lived and died. Civilizations that do not yet exist could emerge, confront the Big Rip, and attempt to respond to it. If you were a civilization with 22 billion years of warning and arbitrarily advanced technology, what would you attempt? Drop your most physically serious answer below. Not the most creative, the most physically plausible, given unlimited time and resources. Next video, Venus, the planet that was once like Earth, what destroyed it, and why the same process has already started here. The runaway greenhouse effect that turned a potentially habitable world into a surface temperature of 465 degrees Celsius and an atmospheric pressure 92 times Earth's. And and what the timeline for the same process on Earth actually looks like. See you there.